started in high school at F, so I continue doing it as F. It makes sense because it's frequency. And again, we're not going to grade you on which variable you put, so just put whatever you're comfortable with, right?
Yeah, you can put like you can call this A for all we care, honestly.
Yeah, as long as you get the variable.
That's the second.
Yeah. And then the speed of light is what? Yes, times 10 to the 8th, and what units? Meters per second, right? So meters per second, those are SI units for velocity. We divide that by our wavelength, which we had to get into meters, right, for this to work out. So we get 1870 times 10 to the minus 10 meters in the denominator. And what do we get as our final energy of each photon? On inserting this, what was it? 1.06 times 10 to the minus 18. All right. And this is going to be in units of joules. So we are good there. And this is really you can think of this as joules per photon, right? So that's the unit that we wanted. Because what we calculated, we used the wavelength of a single photon to calculate the energy of the single photon. Therefore, this is going to be in units of joules per photon. And that's exactly what we needed down here. So we just now we need to take the total energy, divide it by the joules per photon, and we'll be left with units of photons. So how do we convert from gigajoules to joules? Is it? Or are you telling or asking?
No, it's only giga is 10 to the power of 9.
So you're telling. So you're saying that there is 1 times 10 to the 9 joules in 1 gigajoule. We agree? Yeah. Do we agree? Yeah. So remember, mega is 10 to the 6th, giga is 10 to the 9th, and then tera is 10 to the 12th. You'll be seeing all those, maybe. So we get 750.3 times 10 to the 9 joules. All right, so I'm going to go down into the second problem just for extra space. So all we do is take the total joules, which was 750.3 times 10 to the 9 joules, divide that by the joules per photon, which was 1.06 times 10 to the minus 18 joules per photon. And you see that our units cancel out like we wanted, and we get left with units of photon.
So the units of the energy of a photon is joules per photon.
What?
The units for the energy of a photon is joules per photon.
Yeah, so it's really joules, right? Because it's a unit of energy, but because we're talking about a single photon, you can put joules per photon in there. Like, that makes sense. So what do we get upon inserting this into a mathematical instrument? What do you do?
7.07 times 10 to the 29. And that makes sense because if the wavelength is tiny, the frequency is higher.
Yeah.
We're not even finding frequency.
If wavelength, yeah, we're not finding frequency, but if wavelength is tiny, the frequency is high, which means that these are pretty high in energy. But because we have a lot of gigajoules, I mean, it makes sense.
Yeah, we have a shit ton of energy from the photons, so that means we have to have a lot of photons to begin to generate that much energy.
I don't know what I'm doing wrong, but I keep on getting to the -7.
To the -7.
Try putting parentheses.
Because remember, if you just look at your exponents, you have 9, and then when you're dividing by an exponent, you subtract. So 9 minus -18 is gonna actually add, so you should get above 9 for sure. And that's exactly what happens there. So. Question's not too bad, right?
Use frequency.
One over hertz or 1/2 seconds, maybe the same thing.
All right. There's no questions on that one. I think we'll move on to the next one. And Rich will happily work with you as soon as, we'll give you all 3 minutes.
At a timer for 3 minutes.
When are you gonna get a case? When are you gonna get a case?
I just ordered
When? When?
today morning. So
I thought you said you were ordering one back in the day.
I did. Something happened. I take care of most stuff. So I already did today.
Frequency of light.
This is a very possible test question you can ask you. In this exact format.
I think this was on last year or last semester. Banking on these grad students is not doing too well.
Oh, yeah, you're testing.
Hey, what do you? What do you?
No. Which of these is strong? And these are not equivalent.
I guess.
That's pretty soon.
See if your money is up.
Three compounds, I would say compound 6 is the strongest space.
From what?
Why? Because, what's it called? As we know, R groups are electron donating, so we have a lot more R groups here. So there's less possibilities for resonance, making it less acidic, therefore more basic.
Okay. Final answer.
Yep, 6 is the strongest, or if you want me to rank them, 6, then 4, then 5. They all learned that yet?
Yeah, so ionization energy is the minimum amount of energy required to remove an electron, or you can think of it to eject an electron. So when you shine light on, let's just say a metallic surface, any surface really, depending on the energy of the light, if it's greater enough to eject that electron, that's the ionization energy. The definition of ionization energy is the minimum of energy required to eject an electron. Thus, we are telling you that the minimum energy required to ionize cesium is 956 kilojoules per millimole. So we're telling you have a millimole worth of cesium atoms, and it requires 956 kilojoules to eject all of those cesium atoms electrons, 1 electron. What minimum frequency of light is required to ionize 1 cesium atom? How would we go about we are given millimoles, but we don't care about atoms. How would we go from unit of moles to atoms? Yeah, so maybe if we.
I
Maybe,
use Avogadro's number somewhere. Number. And as you all know, that is the good old friend 6.022 times 10 to the 20.
so, work with your units, guys. We are given essentially kilojoules per millimole of cesium, right? And we want to get, you eventually just want to find the amount of energy required to eject the electron from one cesium atom. So we can do that using conversions like that, where we go from kilojoules per millimole, cancel out millimoles using this conversion. And obviously you have to have your associated number there. And then Avogadro's number in the last one. And that will give us the amount of energy required from one cesium atom.
And the unit for Avogadro's number.
Is entities per mole.
So it could be like anything, like you could say 6.022 times 10 to the 23rd chairs are 1 mole chairs. Like the atoms part can be like swapped out for anything. But in this case, since we're dealing with atoms, that's why we put atoms. But
So what happens to kilojoules? It's still there. So it's kilojoules per atom.
for now, yes,
Yeah, per atom.
we're gonna get rid of the kilojoules in a second.
Yeah, how did you cancel the millimoles?
So we can say that, what's it called, 1,000, yeah, we use convertibles, so 1,000 millimoles are 1,000 millimoles, 1 mole. And then 1 mole as 6.022 times 10 to the 23rd cesium atoms. And as Keon said, we do need to get rid of these kilojoules at some point, because you know that the energy of a photon we deal with in like joules per something. Because the Planck's constant is also in units of joules, so that's why we need to get it to joules and joules. So we can say 1,000 kilojoules are 1 joule.
You got it reversed.
Oh yeah, my bad. 1 kilojoule, that's 1,000. So we solve this out, you should get a certain number. If we cancel out our units, kilojoules cancel, millimoles cancel, moles cancel. We should be left with a certain amount of energy in joules per cesium atoms. And what is that certain number?
Nine, five, six, nine, nine, five, six, nine, six, 10 power of 3. That's divided by 1 times 10 power of negative 3, 6.022 to the 3 times 10 power of 1.587 times 10 to the power of negative 15.
10 to the power of negative 15. Is that what both of y'all got? All right, 10 to the power of negative 15. Thank you both of y'all. Joules per cesium atoms. All right. So this is our E, right? Essentially, this is the energy of cesium, or the energy per cesium atoms. This is the minimum ionization energy. So now what we need to do is we need to get frequency of light. So how do we go from energy to frequency? What's the thing that links it together? What equation? HV divided by lambda?
But energy of a photon equals HP.
Yeah, you could just use the E equals HV, or HF or whatever. So E equals H nu or F or whatever you want to call it. So the frequency, right, the nu part is going to be equal to E over H. So we have our E, 1.587 times 10 to the negative 15 joules per cesium atom. And then we have Planck's constant, which is 6.626 times 10 to the negative 34 joules per second. So we do all the fancy mathematics right here. What will we get as our answer?
For that 8 atoms per second. Or is it seconds per atom?
Seconds per atom. Atoms per second would be time. So this is the frequency is the inverse of time.
Well,
2.39 to the 18, or times 10 to the 18.
2.39 times 10 to the 18. And we can just say hertz to simplify this. 2.39 times 10 to the 18 hertz. So what?
Yeah, so this is talking about what the this answer we just got here is talking about what
The ionization frequency.
yeah, so it's talking about the minimum frequency of an electron or of a photon of light that is required to eject the electron of one cesium atom, right? So the minimum frequency of a photon that is required to eject or ionize one cesium atom. Yeah,
And does this answer make sense? Based on our values here. So it should be joules times second, not per second.
yeah. Does that make sense?
I mean, if it's a high frequency, the energy is high, right?
Okay.
Exactly right.
So it makes sense.
It does indeed make sense. You always ask yourself, does it make sense? Like, no, that's not for this class. Like, if you get, like a low wavelength, but you have like a low frequency, doesn't really make sense, right? You gotta, so at least if you screw up, you didn't screw up your common sense. They can take everything away from you, but they can't take away your common sense. All right, any questions on number 2?
so there's like, how does atom cancel out on that last part?
Or it doesn't really, so I just put hertz to simplify it, but really you could write it as like
Atom
seconds per like cesium atoms.
atom per second.
Yeah, an atom per second, like, whatever you want to call it. I always called it hertz just to, make everything easier.
For the energy of a photon, there's 2 ways to find it. That's the HV over lambda, or just H times V, or
No, it's
Really?
HC times over lambda.
times, okay.
Really, they're the same thing though, because we're starting off with this equation, right? E equals HV. So we start off with this equation. So energy equals Planck's constant times frequency. But where the HC over lambda part comes in is now we introduce a new concept. So we say that frequency is equal to the speed of light over lambda, which makes sense, right? Because frequency is like the amount of like cycles per second. So if you have a rate, it's the rate per how much you're going over. So that's how many cycles. So you can substitute this V here into here. So that's where you get the HC over lambda part.
Have y'all learned about the series yet? The hydrogen series?
Lyman, Balmer.
Yeah.
All right. Sounds good. We're gonna do some of the problems that you'll see in regards to those series on the test.
All right, first of all, though, let's make sure we're on the same page here. So this is my poorly drawn nucleus in the middle. This is n equals 1, n equals 2, and n equals 3. Okay, so just to make sure we're on the same page here. N equals 1 is which series? Lyman series. L, Y, M, A, N, N. And what region of light? UV. See, UV region. All right, N equals 2, that is what series? Balmer. So Balmer, and then which region of light? Visible light. And N equals 3, pass check. And what region is that? Infrared. I'm just going to abbreviate that to IR. So Lyman, Balmer, pass check, right? You know your three things. N equals 1, N equals 2, and N equals 3. So you're probably wondering, how will I possibly get asked a question like this? And I'm telling you right now, he loves asking questions like this. Like there's multiple different ways he can ask it. This right here is one of them. So question will go a little something like this. Which of the following energy transitions has the two an easy one first. Highest frequency. Highest frequency.
Well, he hasn't even given you the.
Yeah, so I mean, ordinarily, yes, or ordinarily no, or yeah, the lineman would have the highest frequency, but life isn't that simple, and he doesn't ask that type of question. So here's what it'll ask. So it'll be a bunch of n's that'll give. So I'm gonna give you all 4 options: A, B, C, and D. So option A, n equals 5 to n equals 1. Option B, n equals 6 to n equals 2. Option C, n equals 4 to n equals 3. And option D, n equals 3 to n equals 1. Yeah. C. So you're saying C has the highest frequency.
Yeah, because it has. Oh, I don't know.
All right, let's think about this. So highest frequency, right? What does highest frequency mean? Tiny wavelength. Okay, so you want small lambda. What else do you want?
Left spectrum.
A big difference. Greater difference.
Yeah, pretty much. You want small lambda, more energy. This is what you want right here. So highest frequency, this is the way I like to think about this problem, right? When it's asking me highest frequency, I think about like other stuff that has to do with that. So like highest frequency means small, you have a small wavelength and you have a lot more energy. So
Better the difference anything or better difference less energy out of
the greater the difference, the more energy you have.
between N1 and N2.
All right, here's how I like to explain it, right? This is how I've explained it in semesters past. All right, say for example, you're jumping off a 4-story building and you're jumping off a 1-story building. Which one's gonna hurt more, the 4-story building or the 1-story? The 4-story building, right? So if you go higher, you'll have a lot more energy. So it's gonna hurt a lot more.
What I'm talking about is goes from 5 to 1 and gets B to 1. A is the difference of 4, D is the difference of 2. So A has more energy. So there's a bigger difference.
That's part of it. So you got the more energy part right, but you got to focus on the first bullet point. So we got to focus on the smaller wavelength. Yeah, and that's where knowing your series comes in, because The Lyman series, as you'll know, is in the ultraviolet region. And in the ultraviolet region of the electromagnetic spectrum, will you have what's called tinier wavelength or a larger wavelength? Smaller wavelength, right? Because there's more energy. I mean, literally, the UV rays kill people, like skin cancer and stuff. So right off the bat, we can cross off anything that isn't Lyman series. So that's n equals 6 to n equals 2, and n equals 4 to n equals 2. So this fulfills our small wavelength criteria. Now for the one that has more energy. And as I said, the more story building you jump off of, the more it's going to hurt. So the more energy is present, the higher you go. So now n equals 5 to n equals 1. How much difference is that? 4. And then n equals 3 to n equals 1. How much difference is that? 2. So which one? So now y'all have all the information you need to answer the question. So which of the following energy transitions has the highest frequency? A or D? The answer is indeed A. Do y'all get how I solved that? All right. You want to try another one? Okay, let's do this. Let's make it a bit harder this time. Which of the following energy transitions has the highest wavelength? You know what? Let's make it like a Dr. Armand question. Select all that apply. Select all that apply. And I'm going to say A, B, C, D, E, F, G, and H. It's a very hint type question. So on the highest wavelength, so let's say n equals 4 to n equals 3, n equals 7 to n equals 1.
By highest, do you mean like the longest wavelength?
Yes.
Okay.
Yeah, highest means longest. It's probably the highest. So longest. N equals 7 to n equals 1, n equals 6 to n equals 4, n equals 2 to n equals 4, n equals 3 to n equals 1, n equals 7 to n equals 3, n equals 9 to n equals 2, and n equals 7. I already used the number 7 too much. Let's use n equals 8 to n equals 2. Okay. Now, how many of y'all are intimidated by this many answer choices? Good. At least you're being honest. So you likes to put a lot of answer choices on there, and you got to select all that apply. So
Should get one wrong.
yep, because that's how life works. All right. So longest wavelength. All right. What does that really mean?
Isn't passions? Because passions is n equals 3 and it's infrared, and infrared is on the right side of the spectrum, which means it has a longer wavelength.
Possibly.
Okay.
But you're skipping a step here. So longest wavelength means what in terms of like energy and frequency? Low energy, low frequency. So if you have a long wavelength, you're not going to have much energy. And what about in terms of frequency? You're going to have a lower frequency.
There's a conflict.
Resolve it. What the? Modifications are nice.
Better choose my process.
Okay. Low energy, low frequency. So low E, low F, basically. And then the longest wavelength, as Kihan said, would be the past gen series, right? Because we know the past gen series falls in the IR region. So let's get to crossing out stuff that don't have n equals 3. So no for you, no for you, no for you, and no for you. Now, you'll notice I didn't cross out the ones that end in n equals 4. Why did I not do that? Should I do it? Why? Those are just there to confuse us.
No, I clear your quiz, there's one that said n equals 6, and crossed it out, so I'm just gonna stick with the 3 that I know.
Exactly. Sticking with what you know never hurts. So when you're looking at these, always look for your series. Those are your dead giveaways for these questions. So Lyman, Balmer, Paschen. So the n equals 4s, I am indeed gonna cross them out. So we fulfilled our criteria, right? So longest wavelength means low energy. So in the IR region. So we're in the IR region now. Now we're between A and F. So longest wavelength, as somebody said, means lowest energy. Now, which of these have the lowest energy between A and F?
Hey.
You'd be A, because it's only one. You're jumping off of a 1-story building as opposed to a 4-story.
Right, he does like putting all that apply, but if it's only one answer.
Yep. So, as you all have deduced, A is indeed the correct answer. Any questions on that? Pretty self-explanatory stuff, right? All right. See what else we got on here. What forms? All right, I believe in y'all. I think y'all can do number 3. What form? All right. Let's go over the electromagnetic spectrum. So you can make whatever acronyms you want, right, to remember this. The only thing is, you just have to remember the thing fully for the test. So let's start first. Which form of electromagnetic spectrum has the highest energy? Cosmic rays. Cosmic rays. Then what's next?
Yep.
Gamma rays. Then after that,
X-rays.
X-rays. After that, UV. After that, visible. After that, infrared. After that, microwaves. Okay, after that,
Radar,
radar. And after that,
radio,
radio. And what's the lowest one?
broadcast.
Broadcast bands. Yeah, y'all don't need no. Y'all don't need no sticking out or what's it called? Mnemonic.
So you remember this acronym? So you did remember.
Sounded vaguely Cyrillic, but okay.
Yeah, this is an acronym.
All right. If you want to know what our acronym was, then find out after class. After this.
Chicken is gone.
You're gonna get us in trouble.
Yeah. For that's what was said after class for fear of being monetized.
Chicken is gone. Xylophones, underwear, very.
You can make it out of that at home later. Okay.
All right, but point being, yeah, this is the electromagnetic spectrum. So let's go through some statistics on it. Which one has the highest energy? Cosmic rays. So we're gonna put highest energy. And then which one has the lowest weight? Also cosmic. That was a trick question. Which one has the highest weight? Broadcast. So this is highest wavelength, or we'll put lowest. And then everything else, right, falls somewhere in the middle. The question here: what form of electromagnetic radiation has the lowest energy? Broadcast bands. So yeah, that was basically the electromagnetic spectrum in a nutshell. All right. Yeah, we'll save this for next time. We'll save that.
Have y'all gone over quantum numbers yet?
Not in class, but on Alex, yes.
On Alex, all right. We'll wait till Friday then. Do some quantum number problems.
Then we go into like the beginning of it, class, going over like orbitals and stuff.
They probably touch on.
Yeah.
It's probably in the video side.
Because they're talking about like,
So there you go.
You learned about De Broglie wavelength?
No.
It sounds like the Broglie, Broglie.
we're really about to learn that in the video.
De Broglie. All right, so you learned about De Broglie and quantum numbers, and we'll do those problems next time around. All right, so we took away nothing from today. Remember that the energy of a photon is hc over lambda, or hv, or h nu, or whatever. Know the electromagnetic spectrum. Know your different series, because those are going to be important for an equation later that you're going to learn. I don't know if y'all learned it already, the Rydberg equation.
Yeah, we did.
All right, let's finish off today with a Rydberg equation problem. Let's be a little fun. All right. Blue line is the hydrogen emission spectrum. We're doing problem 10 on here. All right. So blue lines of the hydrogen emission spectrum at particular energy level have a wavelength of 433 nanometers. Calculate the initial energy level at which the photons demonstrate this wavelength. Okay. First of all, what is even the Rydberg equation?
It's RH times 1 over n final minus n initial squared.
All right, so negative RH, right?
Yeah.
Oh, Rydberg.
Negative RH times 1 over n final squared minus 1 over n initial squared. So you have this here. Oh, sorry. So you have this here. Now, what is all of this equal to?
Isn't it 1 over lambda?
That's correct. 1 over lambda. So we have our lambda here, 433 nanometers. Lambda. So we have our RH, which is 1.10 times 10 to the 7 meters to the negative 1. What's our n final?
And then equals 2,
Why is it n equals 2?
because it's invisible. And the Balmer series of n equals 2.
How do you know it's a Balmer series?
Because it was invisible light.
It's indeed. Yeah. Might seem stupid, but you gotta expand everything. So yeah, as David said, the final is indeed n equals 2. So now our task here becomes to solve for the n initial. Our wavelength. Now, for the question of that, should we leave that in nanometers or convert it to meters?
Even there.
Are you sure?
Converted to meters, because RH is.
Yep.
Yeah.
Your wavelength you should convert to meters. Because this over here, here's what'll happen, right? So at the bottom here, you have meters, and then this is meters to the -1. So then, yeah, your units will have a fun time. All right. So 1 over lambda here is going to be equal to 1 over, and then I'll just leave it like this, 433 times 10 to the